Welcome to this technical briefing by S.K. Srinivas on the advantages of core shell columns.
All right, let's dive right in. We're going to start with a fundamental challenge that, every single one of us in chromatography faces. It's that constant balancing act, right? The push for higher resolution versus the very real physical limitations of our equipment.
So traditionally, the choice we had was pretty stark. On one side, you've got your standard 5-micron fully porous particles. They work just fine on our conventional HPLC systems, right around 400 to 600 bar. But the resolution, it's okay but not great. Then on the other side, if you really want to crank up that resolution, you move to sub-2-micron particles. And they're fantastic for resolution, but here's the kicker. The back pressure goes through the roof. It's way more than a standard HPLC can handle, which means you're suddenly needing to invest in specialized UHPLC hardware.
So this exact dilemma, this pressure problem, is what really pushed the science forward. It forced us to completely rethink the particle itself, and that led to a really elegant innovation in how we design the stationary phase.
And that brings us to superficially porous particles, or SPPs for short. Now, instead of being completely porous all the way through, these particles have this really clever hybrid structure. Think of it like this. There's a solid, non-porous core right in the middle, and then it's wrapped in a thin, porous shell of silica. It's kind of the best of both worlds.
And this architecture is an absolute game changer when it comes to mass transfer kinetics. See, the analytes interacting with the stationary phase, they only have to diffuse through that thin outer shell, not the whole particle. This dramatically shortens their diffusion path, and that has some really profound implications for our chromatographic efficiency.
Okay, so here's where it gets really interesting, especially when we look at the Van Deemter equation, the thing that describes our band broadening. That solid core, it helps the particles pack in a more ordered, uniform way, and that cuts down on longitudinal diffusion. That's our B term right there. At the same time, because that diffusion path is so short, it minimizes the resistance to mass transfer, which is our C term. So by tackling two of the main causes of peak broadening at once, we end up with a huge boost in overall efficiency.
So, all this talk about Van Deemter efficiency is great, but what does it actually mean for us in the lab? What's the practical payoff? Well, the results are pretty dramatic, and they take us right back to that initial problem we talked about.
Okay, get this. For the same level of efficiency, these core shell columns generate way less back pressure than those sub-2-micron fully porous particles. We're talking a reduction of about 50%. That is huge. And really, this is the key takeaway. It means you can now get that ultra-high performance, that sub-2-micron level of efficiency, but you can do it on the standard 400 to 600 bar HPLC systems you already have in your lab. You don't need to go out and buy expensive, specialized, ultra-high pressure hardware.
And this is a fantastic illustration of the real-world impact. What we have here is a direct side-by-side comparison under the exact same conditions. The chromatogram from the core shell column just pops. The peaks are so much sharper, so much narrower, and that translates directly to what we're all after: higher resolution and better sensitivity.
Okay, so this all sounds amazing, right? But to really get all the benefits from this incredible efficiency, there is one critical thing about our system that we absolutely have to pay attention to. You see, because these columns produce such incredibly narrow, low-volume peaks, anything outside the column that adds to band broadening, what we call extra column volume, suddenly becomes a much bigger deal. We're talking about tubing, connections, the detector flow cell, all of it. To make sure you don't lose the efficiency gains you just worked for, you've got to minimize that extra volume. This is especially true if you're working with narrow-bore column. All right, now let's switch gears a bit and tackle some of the most common, practical questions that chromatographers have when they're thinking about moving to this technology. We'll do a quick rapid-fire FAQ.
Okay, question number 1, and it's the big one. Is my standard HPLC system compatible? Can I even run these things?
The answer is an absolute, definitive yes. In fact, that's the whole point. They were specifically designed to bring that sub-2-micron performance to all of us using standard HPLC systems. The ones that top out around 400 to 600 bar.
All right, next up is a really valid concern. With that solid core in there, am I going to lose loading capacity?
The impact is actually minimal. Yes, the porous volume is a little bit smaller, but here's the trade-off. The efficiency is so much higher that your peaks get taller and sharper. This jacks up your signal-to-noise ratio. So what often happens is you can inject a smaller sample volume and still get better sensitivity than you would with a fully porous column. It really balances itself out.
Okay, another critical question, especially for any busy lab.
What about durability? Are these things as tough as fully porous columns?
Believe it or not, they're often more durable. That solid core gives the particle a really rigid structure. This leads to a much more stable, uniform, packed bed that's better at handling pressure shocks. The bottom line? You often get a longer column lifetime, especially if you're running at high flow rates.
And finally, this is a big one for anyone with validated methods they rely on. How hard is it to migrate my existing methods over to a Coreshell column? Honestly, the process is pretty much seamless. You can use the exact same mobile phases, the same organic modifiers, everything. The only thing you'll really need to do is adjust your flow rate a bit to find that new sweet spot to take full advantage of the much flatter Van Diemter curve that these particles give you. It's that simple.
So that wraps up our technical briefing on Coreshell technology. I think the key takeaway is really clear. This is a powerful way to unlock incredible efficiency without having to go out and buy new high-pressure hardware. So the final question I'll leave you with is this. What analytical challenges in your lab could you solve with that kind of capability?